Hello friends, welcome to my channel. This is Thermodynamics and Power Plant Part 5. Question is, an increase in pressure of a liquid from 7.5 megapascal to 15 megapascal results in 0.2% decrease in its volume. The coefficient of compressibility of the liquid in meter square per Newton is, we have to calculate that one, kT. And one more thing we know, bulk modulus K equal to del P by del V by V. And coefficient of compressibility Kt is 1 by K, 1 by bulk modulus. So it will come or 1 by V into so in this question data given are P1 is 7.5 MPa megapascal or 7.5 Newton per mm square. In answer he is asking in meter square per Newton. So you convert it into 7.5 into 10 to the power 6 Newton per meter square. Then P2 it's 15 into 10 to the power 6 Newton per meter square. So change in pressure is 15 minus 7.5 is 7.5 into 10 to the power 6 Newton per meter square. Del V is 0.2% or 0.2 by 100 of initial volume V. So it's 0.002 V. We have to calculate Kt. So Kt equal to del V 0.002 V by V into 7.5, 1 by 7.5 into 10 to the power 6. V cancel. Then it's 2 by 10 to the power 3 divided by 7.5 into 10 to the power 6. So here we can write this one 2 by 10 to the power 3 into 10 by 75 10 to the power 6. So 20 by 75 or 5 into 2 15, 4 by 15 into 1 by 10 to the power 9, then 0.2 then 6 into 10 to the power minus 9 meter square per Newton. So from option 0.26 into 10 to the power minus 9. A is our answer. A reservoir of capacity 0.01 meter cube is completely filled with a fluid of coefficient of compressibility 0.75 into 10 to the power minus 9 meter square per Newton. The amount of fluid that will spill over in meter cube if the pressure in the reservoir is reduced by 2 into 10 to the power 7 Newton per meter square. Here capacity B is 0.01 meter cube. coefficient of compressibility. Kt is 0.75 into 10 to the power minus 9 meter square per Newton. The amount of fluid that will spill over, del V you have to calculate, and del P given 2 into 10 to the power 7 Newton per meter square. Same formula as previous one we have to use. So put the values. Zero 0.01 into del V we have to calculate. Kt is 0.75 into 10 to the power minus 9. Del P is 2 into 10 to the power 7. So del V is 0.75 into 0.01 into 2 into 10 to the power 7 by 10 to the power 9. So 10 to the power 7 by 10 to the power 9, 100. Then 0.75 is 75 by 100. It's 1 by 100 into 2 divided by 100. So 150 by 10 to the power 6. So it's 15 by 10 to the power 5, or 15 into 10 to the power minus 5. So from option 15 is not available, all are in 10 to the power minus 4. So 1.5 into 10 to the power minus 4, unit is meter cube. So from option 1.5 into 10 to the power minus 4, B is our answer. Question is, water is boiled at 1 into 10 to the power 5 Pascal pressure in a coffee maker equipped with an immersion type electric heating element. The coffee maker initially contains 1 kg of water. Once boiling started, it's observed that half of the water in the coffee maker evaporated in 18 minutes. If the heat loss from the coffee maker is negligible, the power rating of the heating element. Pressure P equal to 10 to the power 5 Pascal or Newton per meter square. All options are in kilowatt, kilojoule per second. So initial mass is 1 kg. Half of the water evaporated. So M2 is 0.5 kg. Time is 18 minutes. Option is in kilojoule per second. So 18 into 60 second. Power rating we have to calculate. We know heat supplied to evaporate water equal to Q, and Q is mass into enthalpy of vaporization. Here enthalpy of vaporization we have to remember, H equal to standard value is 2250 kilojoule per kg Kelvin. Kilojoule per kg 2250, this one we have to remember. Sometimes they won't give you. So standard value you just remember. Then Q equal to mass is 0.5 kg or 1.5 into 2250 enthalpy, it will come 1125 kilojoule. Power equal to Q by time. So 1125 divided by 18 into 60. So it's 12, then 25 by 24. It's 1.04 kilojoule per second, or it's kilowatt. Nearly 1.05 kilowatt. So from option C is our answer. Next question. Zeroth law of thermodynamics is not valid for the following. Case 1. First, a 50 ml of water at 25 degrees Celsius is mixed with 150 ml of water at 25 degrees Celsius. It's not valid. Water mixed with water, so it's valid. 500 ml of milk at 15 degrees Celsius is mixed with 100 ml of water at 15 degrees Celsius. Water we can mix with milk. So B also valid. 5 kg of wet steam at 100 degrees Celsius is mixed with 50 kg of dry and saturated steam. This one also valid. 10 ml of water at 20 degrees Celsius is mixed with 10 ml of sulfuric acid. H2SO4. Water plus H2SO4. Here chemical reaction will occur, so this is not valid for zeroth law of thermodynamics. So D is our answer. When air expands from initial pressure P1 and volume V1 to final volume 5 V1, following the law PV to the power n equal to constant, here greater the work done and n value we have to use. We'll start from 1, direction is this direction. It expands from V1 value to 5 V1. So here in this case we know constant pressure process n equal to 0 and constant volume process n equal to infinity. Here n is less than 1 and here n equal to 1 for isothermal process. And n equal to gamma for adiabatic process. So from all the options we have to check. Greater the value of n, greater the work obtained. Greater the value is n equal to infinity. Here work is 0, so A is not possible. The area under PV diagram it shows our work done. So wherever area will greater, their work will be higher. Smaller the value of n, smaller the work obtained. Smaller means n equal to 0, their work obtained is higher, greatest. So this one also not possible. For n equal to 0, the work obtained is greatest. So this one is possible. Isobaric or constant pressure process. This process gives highest work done. For n equal to 1.4, this one, gamma equal to 1.4. Work obtained is greatest. No, this one is less than that isothermal and constant pressure process. So D also not possible. C is our answer. air is compressed to half the volume at constant pressure, then the change in entropy. Two graphs I will show you. From that graph we can answer this question. One is PV, pressure versus volume. Next one is temperature versus entropy. Air is compressed, so at constant pressure from 1 to 2 to half the volume, let it be V or V1. Here V2 equal to V1 by 2, half of the initial volume. Then temperature in entropy, temperature and entropy diagram, we can see the entropy, how it's behaving. The diagram will like this, from 1 point to 2 point. Entropy is S1 and S2. From this graph we know S1 is greater than S2. So entropy S is decreasing in this compression process. So change in entropy decreases. B is our answer. A cycle is shown below on PV diagram. PV diagram shown. In TS diagram how it will come, we have to check. Here BC is constant pressure process and AB is adiabatic process and AC is constant volume process. So from option method of elimination we will apply here. AB is isoentropic process and AC is isothermal process, but AC is constant volume process. Here AC is constant volume, so A is not possible, and in this case B may be possible, so go for C. AC is isothermal, but in PV diagram it's constant volume, so C also not possible. Then BC is constant pressure process, here it's isoentropic, so BC also not possible. C is not possible. Then D. In D, AB is adiabatic process, here it's isothermal process, so D also not possible, only B is possible. AB is isoentropic or adiabatic, it's correct. Then BC is constant pressure, possible. AC is constant volume, this is also possible, so B is our answer. If 2 bar of air at 27 degrees Celsius is heated to 177 degrees Celsius at constant volume, the pressure will be how much? Constant volume process. Constant volume heating. P1 is 2 bar, T1 is 27 degrees Celsius is 27 plus 273, 300 Kelvin. Then T2 is 177 degrees Celsius plus 273, 177 plus 273 come 0, 450 Kelvin. We have to calculate the final pressure, V1 equal to V2, constant volume process. So combined gas equation, P1 V1 by T1 equal to P2 V2 by T2 V1 constant, so cancel. P2 is T2 by T1 into P1, so T2 is 450 by 300 into P1 is 2 bar, so 15 into 2, 15 into 3, 2 cancel, it's 3 bar. So from option B is our answer. Question is, a frictionless heat engine can be 100% efficient only if its exhaust temperature is a heat engine. This is heat engine. This is source, maximum temperature Q1, heat supplied to the heat engine from the source, and here it's sink at minimum temperature. This is heat rejected from the heat engine to the sink. Here work done. Work done is the output, and this is source. In this question, frictionless heat engine can be 100% efficient. Efficiency of heat engine is work done by heat supplied. For Carnot heat engine, it's T max minus T min by T maximum. So it will be 100%. If T max will be 0, it will 100. T minimum will 0. Then efficiency of heat engine is T max by T max equal to 1 or 100%. So T minimum equal to 0. Exhaust temperature, this one, T minimum is our exhaust temperature is 0. It's not possible. B also not possible. C is 0 degree Kelvin, D is 0 degree Celsius. If we will give 0 degree Celsius, then in Kelvin it will come 273 Kelvin. But if it is in 0 degree Kelvin, then T minimum will be 0. So C is our answer. An ideal engine absorbs heat at 127 degrees Celsius and rejects at 77 degrees Celsius. The efficiency is how much? Again I am drawing that heat engine. This is source, T maximum, heat supplied is Q1, heat rejected from engine is Q2, sink temperature is T minimum, here output is work done. We have to calculate the ideal engine efficiency or Carnot efficiency. Efficiency of heat engine, ideal, work done by heat supplied, it's T maximum minus T minimum by T maximum. So T maximum is 127 degrees Celsius. 127 plus 273, it's 400 minus T minimum is 77 plus 273, it's 350 by 400. So 50 by 400. So 0, 5 by 40 is 1 by 8. In percentage, ideal efficiency is 8 into 100. So it's 12.5. 12.5% or equal to 13%, nearby 13%. A is our answer. For the same compression ratio, the thermodynamic cycles in the order of decreasing efficiencies are Otto cycle, dual cycle and diesel cycle. We have to compare for same compression ratio. So we will draw the graph. PV, here same compression ratio, so this is clearance volume VC and this is stroke volume. We know compression ratio VC plus VS by VC. So for Otto cycle, first we will draw. It will come like this. One, two, 3, 4. And for diesel cycle, same compression ratio, so it will come from here. One, two, 3, 4. And for dual cycle, come like this, 1 to 2, then 2 to 3, 3 to 4, 4 to 5. The order of decreasing efficiency. So highest efficiency is Otto is greater than, dual is greater than diesel. So from option D is our answer. Otto greater than dual, dual greater than diesel. Here in this graph, area of Otto cycle is greater than the area of dual cycle and area of dual cycle is greater than the diesel cycle. So efficiency of Otto cycle is greater than efficiency of dual cycle and efficiency of dual cycle is greater than efficiency of diesel cycle. A room containing 60 kg of air at 100 kPa kilopascal and 15 degrees Celsius. The room has a 250 watt refrigerator. In bracket, the refrigerator consumes 250 watt of electricity when running, bracket close. A 120 watt TV, a 1 kilowatt electric resistance heater and a 50 watt fan during a cold winter day. It's observed that the refrigerator, the TV, the fan and the electric resistance heater are running continuously, but the air temperature in the room remains constant. The rate of heat loss from the room that day is how much? The rate of heat loss we have to calculate. First we have to calculate the total appliances. How much? Its first is 250 watt refrigerator, then 120 watt TV, 1 kilowatt is 1000 watt electric heater, then 50 watt fan. Total wattage is 1420. 20 watt. Then mass of air is 60 kg, Then temperature of the room is remain constant. Rate of heat loss from the room we have to calculate in that day. So it's 1420 watt is joule per second. So in our option it's kilojoule per hour. So 1420 by 10 to the power 3 into second to hour 3600. So 10 to the power 3 here 30 cancel. 142 into 36. 142 into 36. If you multiply this one, 142 into 36, we will get kilojoule per hour, 5112. So from option C is our answer. Efficiency of Carnot engine is given as 80%. If the cycle direction is reversed, what will be the value of COP of reverse Carnot cycle? First one is heat engine, Carnot engine. Source, maximum temperature. This is maximum temperature, T max. Q1 is heat supplied to the engine. Sink temperature is T minimum. This is source. This is sink. Q2 is the heat rejected from engine to sink. This is work done. When cycle direction reversed, it will act as a refrigerator. Here, from here we will draw the heat. T minimum sink temperature. Here it's T maximum, Q1, and this one is Q2. Work is done on the system. This is refrigerator. Heat engine is clockwise, refrigerator is anti-clockwise. And here efficiency is T max minus work done by heat supplied by T maximum. Here COP of refrigerator is refrigerating effect or desired effect by work done. So COP of refrigerator is refrigerating effect is T minimum by work done is T maximum minus T minimum. And if it is a heat pump, COP of heat pump equal to COP of refrigerator plus 1, and COP of heat pump is desired effect is T maximum or refrigerating effect is T maximum divided by T maximum minus T minimum. One more thing is important here. Efficiency of heat engine into COP of heat pump equal to 1. This one and this one. If we multiply, we will get 1. Here in this question, efficiency of heat engine given as 80%. This one given efficiency of heat engine equal to 80% equal to 0.8. So from here COP of heat pump we can calculate. Heat pump equal to 1 by efficiency of heat engine. So 1 by 0.8 or 10 by 8. 10 by 8 is 5 by 4 or 1.25. And one more thing we know, COP of heat pump is equal to 1 plus COP of refrigerator. In this question we have to calculate COP of refrigerator. It's COP of heat pump minus 1. 1.25 minus 1. So it's 0.25 COP of refrigerator. This is our answer. When Carnot engine is reversed, it will act as refrigerator. So COP of refrigerator is 0.25 from option C is our answer. Thank you friends. Thank you for watching my video. Thank you.